All right. Our next speaker is Michele Titolo. It is also a distinct pleasure for me to introduce her. She has worked at Capital One. She maintains an application that uses services that's used by 10 million people, I believe. Is that more than 10 million people? Okay, that's microservices at scale. And has a JD Power rating of more than 4.5 stars, I believe. So this is not only something that's used by a bunch of people, but actually is liked by a bunch of people, which is, in my experience, unusual. She also has contributed greatly to iOS and lectures regularly on features of Swift and other languages and development aspects for mobile platforms. So she has a variety of experience both in microservices and in deploying on the mobile devices. So let's welcome Michele.
Okay, good morning. Is this thing on? Yeah, great. So thanks, Mike, for the introduction. As he said, I'm a lead software engineer over at Capital One. I specifically work on building applications that work and support our consumer-facing products. So if you use the Capital One iOS app, I did a whole bunch of work on that before coming to this team, which I now support, as well as the Capital One Android app and the Capital One website. So I build services that scale. And my team does use microservices architecture. And as Chris said, I was actually really excited as Chris was giving his talk because he laid a really great foundation for me to now talk to you a little bit more about the day-to-day operations of your microservices and the kinds of things that you need to know in order to operate your microservices at scale. So as Chris mentioned, microservices are really a distributed system. You don't just have your one monolithic application that has everything in it. You have a bunch of different pieces talking with each other and who together as a whole represent what you're trying to build. Now, it would be really, really nice if this was like a really tree-like system where things just kind of go one to another, because this is really easy to understand, right? But in reality, microservices look a little bit more like this. There are definitely interdependencies. There are some services that are much more central to your system than others. And there are going to be services that are only really used every once in a while. And one of the big things to realize is that when you're deploying microservices and you're operating microservices, something will probably go wrong. And this might not be something that you do. It might be something else entirely, like a subnet splitting. But designing your microservices system for failure helps you operate with more confidence, and it ends up leading to more success. So there are a couple questions that happens when you're trying to work with microservices. If you have this really big distributed system, how do you actually figure out what's going wrong? How do you deploy a fix in a way that doesn't make the system have any further problems? So microservices are all about new operational challenges and new infrastructure challenges. And this is because, as Chris said, microservices are a lot more about application size. It's not just about having a service that's only a few thousand lines of code versus 750,000 lines of code. It's about creating a much larger system. And so you have significantly more failure points, like so many more failure points, because everything that's not happening within that one little application becomes a failure point, a potential failure point. And so what this really means is microservices need an ecosystem around them in order to thrive and in order to be up and readily available. And this is something that the individual applications have to contribute to. You can't just deploy out Kubernetes and expect applications to work fine on Kubernetes. That's just not going to work. Applications have to be updated. But you also do need to update your infrastructure as well. So it's a two-part problem. Otherwise, you'll keep playing catch-up. I've seen systems where they don't have fully automated deployments, and oh my God, it takes forever to deploy a microservice. It's the same amount of time. I've seen systems where you can't automatically create databases at deploy time. Again, it takes forever. I've seen systems where, oh, the log forwarder wasn't working, so now we have to SSH into a server to find logs. You're not going to want to do that in microservices. And so there are three really big challenges when you're moving to microservices or just working with them for the first time, or you're really early on in your microservices exploration. The first one is deployment. Deploying microservices is a bit different. The second is scaling. Because microservices are a distributed system, not all of your microservices will be having the same load. Different parts of the system will need to handle more traffic, and there's going to be some parts of the system that don't really get used very often. And lastly, but certainly not least, debugging. You have, instead of one application to debug, you now have dozens or potentially hundreds of applications that might be causing some sort of problem. So all of these challenges together, when they're handled appropriately, create a solid foundation that allow microservices to really thrive. So, first up, let's talk about deploying. What are the characteristics of microservices deployments? Well, you generally have small releases. You might initially release a code base that's smallish, but then you're going to be iterating faster, because microservices are all about doing things fast, and that usually means smaller pieces of code going out at a time. Frequent releases, again, microservices are all about speed. But you also need to have consistent releases. If you're going to be releasing multiple times a day, you don't want each one of those releases to be different than the ones that happened before them. You want everything to happen in a very similar fashion. And you want to really limit those special snowflakes. Everyone has one of those systems that's just a little bit different for totally valid reasons, but you want to limit those because that adds to your deployment time, that adds to your operational complexity, and whenever someone new comes in, you have to explain to them, like, everything is the same, except for that one thing over there. And that just adds to the complexity of your system. So deployments for microservices really, really, really depend on your tooling. And while you might not want to build all of your tooling up front, assuming you know what your tooling needs to look like, you definitely want to invest the time and resources into building tooling to help you automate every single aspect of your deployment, literally everything. Everything from database creation, provisioning, building your artifacts, all of that stuff has to be automated. And automated in such a way where you don't necessarily need human interaction. You should be able to merge a pull request, and then magically deployments happen, and then they go into your staging environment or into production if you're running one of those really fast and highly available systems. But that's not to say that it should always run and it should be an unstoppable train, because things are going to go wrong. If you're in the middle of an incident, you might not want people deploying. So building a system that is fully and completely automated, but has those stopping points where you can say, oh, we don't want to deploy this thing right now, let's put it on pause, figure out this other issue we're dealing with, and then continue with it later is also really important. So when it comes to deployment strategies, it all really ends up coming down to one pattern in my experience that works the best with microservices, and this is staged deployments. This is, again, infrastructure heavy. Most of the stuff I'm going to talk about requires new and more sophisticated infrastructure. But there's two different kinds. The first is a canary deployment. This is a kind of deployment that rolls your changes out really slowly. So all of this depends on some sort of router at the front of your services. It's pretty standard in microservices. You're not usually going to have only one instance of a service, so you need something in front of it, load balancer or a router to route traffic. So in a canary deployment, you have your router, and you deploy one new instance of the server, and you send traffic to it. You start with like a really small percentage, 1%, 5%, you ramp up, you ramp up. If things look bad, you roll back. And the benefit is, you only saw failures in that 1% of traffic or that 5% of traffic. And it happens early. So most of the people using your system aren't affected if this is a bad change. But if it looks good, you keep going. And you roll out new instances of the new version, again, and finally, you're running all new instances of all the new version of code, and you're good, and you're done. There's another kind of deployment called blue-green. This one, I know I've also seen done in data centers because when you don't have the provisioning tooling on like AWS or any public clouds, this is a little bit easier. Blue-green is the term that my team has used for this, but red-black is also popular. Netflix loves doing things with red and black. So if you ever read any of the Netflix open source documentation, they love red and black. So this is similar where you have some sort of router in front of your microservices. You deploy a duplicate set of applications. So now you have 2 sets of applications running. And then you move traffic from the old set to the new set. This is usually a 100% cutover. There are some systems that let you do split traffic 50-50, but one of the reasons that people like this is because you can go back really, really easy. You can flip back to that other channel and everything's fine. And both of these allow you to do automatic rollbacks, because if you're deploying frequently, there is a little bit of a higher chance that something's going to go wrong because things happen quickly. But automated rollbacks mean that you're going to have the least amount of downtime and the least amount of impact on the people ultimately using the system. So this brings me to another question of, when you're deploying stuff, how do you know a deployment is successful? Like, this is one of the things that people tend to talk about, like, oh, a successful deployment, a successful deployment. Well, have you ever actually sat down and wrote out a list of items that means a deployment is successful? Most people haven't. We just kind of know intuitively what that means. And so when you're thinking of a successful deployment, a lot of this revolves around features and tooling again. So for your application, you have some sort of tests passing. That's a good thing. You have to have an application health check up and running so that the application can report that, yes, I'm ready. The only thing that the application knows all of its intricate details. So I'm going to talk about health checks a lot. And so it's the only one that can really say whether or not it's able to receive traffic. And then you need to handle dependency and secret injection. So testing, really robust tests. Testing, as Chris already mentioned, is incredibly important when you're building a big system because you have more points of failure, you have more applications, and you need to be able to have confidence that everything's working appropriately. So this is both unit and integration tests. Unit tests for correctness and integration tests for checking that this thing can work with this other thing really well, and it has the same contract it said it would, and that it can connect to the database, and the integration tests are end up becoming part of your deployment pipeline. And because you're doing really frequent deployments, you're also going to be doing frequent testing. So you need to design your tests in a way that they can be running several times a day and not have any issues. If one of your tests is about making database changes, you need a way of either using a test database or having some way to roll those changes back so that you can continually update and run these tests. All of your applications need a standardized health check. I'll get to the standardized portion in a minute. But applications reporting on whether or not they are ready to receive traffic is one of the baseline requirements because they're the only ones that know if they're healthy. Well, other things do too, but they're the only ones that are actually able to confidently say, I'm ready. Consuming dependencies and secrets. And what do I mean by this? So dependencies, like, what's the URL to your database? Think about it. If you're running a deployment pipeline that's going from, a merged pull request to production in, let's say, an hour, it's going to go through some pre-production environment. It might go through some testing environment, and then it's going to go to production. You're going to have 3 different databases in that pipeline, and you don't want to be going in and making a code change every time your service needs to talk to a different database. So being able to inject that information into your service makes it a lot easier for things to go through. And also secrets. Please don't hard code usernames and passwords in your applications. I hope everyone in here has not done that. I've seen it happen, especially when you don't have the tooling in place to help with this. Because you have a QA password for a database, you have the production password to the database, and of course, the more times these passwords are stored in plain text, the less secure they are. So please don't do this. And make sure you have a system set up. It is more integration points, but it provides a lot more resiliency, especially in the case that a password is leaked. If all of your applications are consuming that password from somewhere else, they'll all get updated automatically. And you don't have to worry about going back, changing the code, testing the code, and deploying a fix. It'll just happen on its own. So test passing, health checks, and dependency and secret injection are kind of the 3 things that the application relies on for determining whether or not a deployment was successful. But there's also a system level part to this, because you might just be deploying one application, but that application is part of a larger system. So you need to have some sort of system to aggregate your health checks. And this is where that standardization of health checks comes in. Because if you're running 100 different services, you do not want 100 different health check formats to be using. You want everything to be consistent. And all of this because you want to be able to see your overall system state. We're not just looking at individual applications anymore. You need to know that did we deploy this new version of this thing and another part of the system start failing? You don't want that to happen. So you need an overarching view of system state, which is mostly relying on those application level health checks. And then the system also needs to have a way to determine whether a deployment was successful or not. It's not just a human that needs to know, it's the system itself that needs to know and understand. So the system needs to have a definition of successful, which can be read by computers. So this shouldn't be someone just like sitting at a terminal, just like redoing curl commands until they get a 200. This needs to be fully automated. I've also seen that happen. And your deployment system also needs to be proactive because you don't want someone sitting and repeating a curl command. And your system needs to be able to report on deployments. So if there's a deployment ongoing, people should be able to see the current status. Because even though you're working in small teams, when you're working on a system that is really interconnected, loosely coupled, but interconnected, other people are going to need to know about your deployments as well. Your people on your team are going to need to know about your deployments, and especially if something goes wrong, you want to be able to see a history of, okay, well, we were able to build our code, we were able to put our code on the server, but then the server wouldn't start. You need to know that history in order to figure out what went wrong with the deployment. And then if you're really, really interested in going for the gold star, you can do something much more interactive like bots. I actually used to work at Reddit, and they had this really great deployment system that was all IRC-based and then Slack-based. So there was one big channel, there were only 40 developers there at the time, and deployments would go on in the channel, so every single person had insights into what was going on, and if something went wrong, the person who started the deployment got a mention and it was automatically rolled back. And it worked really, really well because everyone had insight into the system, and there was even a queuing system because Reddit at that time was a monolith, so you had to deploy the entire thing at once. So you were able to be like, I want to deploy next, but so-and-so's deploying, so their deployment goes first and then yours. It was really nice, gotta say that. So, to recap, deployments are about creating tooling and infrastructure that help you understand when your applications are finished deploying. And being finished depends a lot on the system, depends a lot on your individual applications, and it depends on your overall system state. So once the deployment's finished, you're done, right? That's all you care about. Your application's up and running, and it's perfect. Nothing's ever going to change, right? No. Distributed systems are constantly in a state of change. One of the benefits of microservices is loosely coupling different parts. So if one service is getting a ton of traffic, you have login services usually end up being these kinds of applications where every other application depends on login. So if login goes down, everything goes down, which means login is getting a lot more traffic than everything else. And you don't necessarily want to be spending thousands upon thousands of dollars a month making every application in your system have as much potential for load as your login system. They're going to be unbalanced. Some services will be getting lots of traffic, some will be getting a little bit of traffic. And this is where scaling comes in, because the traffic that you get in a microservices system is uneven. Applications will have more load, and applications will have less load. And your system needs to understand this. Your system needs to be able to reason about this and say, oh, hey, requests are spiking to this one application, we need to react. As well as conversely, oh, this application isn't being used much, why do we have 6 Amazon EC2 instances that are costing us $3,000 a month? That's $18,000 a month for something that's basically not getting used. It allows you to be a lot more cost effective. And this all, again, comes down to health checks and tracking application health. So that you're looking at things like CPU, RAM, latency, requests per second. All of these kind of simple metrics help you understand whether or not an application is going to be able to handle even more traffic. And of course, there's also going to be some custom things. So even though you don't necessarily want any special snowflakes in your system, you can create classes. So databases will probably have a certain set of metrics, and they'll report on reads and writes. Things like Redis and Memcache that are cloud or key value stores, those are going to have different things. If you have an event bus like a Rabbit cluster, that's also going to have a different set of metrics. But overall, you're still going to want to know latency on those. You're still going to want to know RAM and CPU on those. So it's all about capturing that information. All of this coming down to how do microservices actually scale? Automation is the name of the game. If you're scared of automation, get more comfortable with it because you're going to need to do it for microservices. And not just any automation, because automation that needs to be really, really smart. It needs to be able to understand what's going on. Not smart in like an AI sense. Those are hopefully way in the future, but smart as in like it can do really basic reasoning. Because your system needs to be able to trigger some sort of scaling event automatically. You don't want someone sitting, looking at some dashboard, seeing, oh, we just had like 100, we're just getting 90% CPU activity on the servers. Let me push a button to scale it up. It turns out computers are really great at numbers. Yeah, so something that can be numbers-based, which most of your metrics can be, it's really easy to write a trigger for some sort of scaling event to happen. And this is for both scaling up and scaling down. People talk a lot about scaling up, but I also want to make sure people understand to also scale down, because if you're in a public cloud environment, that's costing you money. And I work for a bank. We have lots of money, but even then, you don't necessarily want to be wasting thousands upon thousands of dollars a month running servers that are not being used. It's just like basic business 101. Don't have extra money, like don't waste money. So what happens when you're scaling up? Well, scaling up, it turns out, is really easy because I just talked about it, and it's just deploying a new one, new application. The same way that you deploy something from like a pull request, a lot of that automation can be reused when you're scaling up or down, or scaling up specifically. So you create a new instance using hopefully whatever automation you already have to deploy instances, and you monitor your health checks, again, because this is a new instance. If this application has been running for 2 years and it's never had a problem, but suddenly you need to have more of it, it should just work. But something might change, so again, you're monitoring your health checks. And of course, you have some router or load balancer sitting in front of your services that will send traffic to it once it says it's okay. Deploying new instances for scaling is a lot like deploying new instances in the first place. Scaling down is the part that usually trips people up, because people are always thinking about creating. Destroying is actually just as important, because remember, when you're deploying a new version of the application, the old versions are going away. So in essence, those are being scaled down to 0. So this will happen a lot of the time when instances aren't being used, whether there's actually a new deployment going on, same automation, or if you realize that, oh, hey, we're wasting thousands of dollars a month, let's not have as many instances of this thing running. So first part of deployment automation for scaling things down is stop sending traffic to it. It seems kind of obvious once you think about it, but if you're trying to tear something down and it's still getting new traffic, it's going to have new work to do. So you want to not give this application any more work. You want to like just not give it more work, but you also want to let it finish the work that it's already done. If there is some outgoing request from this service to another one, you want to let that finish, because you don't want to just like cut everything off and then return errors. All of this talk is about not having errors. So you want to be able to have the service that is about to be shut down finish the work that it's doing in a nice way and like completely get like I'm no work done, including things like queuing systems. This system also needs to disconnect. If you're connecting to a database, gracefully disconnect that. If you're connected to a real-time messaging system like a Rabbit cluster, you're going to want to send the appropriate close messages. And this is important because a lot of systems that use real-time protocols, if you don't send the appropriate close message, they'll get an error the next time they try and send a message to your application. So it's really important to understand the closing procedures for everything that your application talks to. If you're just dealing with a REST-based system, your life's a lot easier. And of course, reporting this progress is important. If you have an application that is managing a queue of things to do, and that queue is not getting any smaller, you need to be able to see that in your health checks, because that means that this application is never going to shut down because it's stuck. And it needs to be able to report which part of the scaling down it's doing. If for whatever reason this application can't disconnect from the database, sounds weird, but it might happen. You also need to be able to see that, because then you're going to need to do some manual intervention to actually make sure that this thing goes away. And then ultimately, when this application has no traffic, it has no work, and it has no connections, then you can actually remove it safely. All of this is about making sure that the system is ready for that application to go away. And I've talked about routing traffic, and I mentioned routers and load balancers. These are pieces of your infrastructure that you really need. And they're really, I've said routers and load balancers, but Chris also mentioned another thing called service discovery that works pretty similarly. So I'm going to talk a little bit about what these are and some of the similarities and differences that they have in particular relationship to scaling, because at the end of the day, when you're deploying, they work pretty similarly. So load balancers. These are actually built in with all of your public cloud providers. So if you're using AWS, Google Cloud, Azure, they all have a really nice one built in. Things like Kubernetes have one built in, and a lot of the other smaller PaaS providers also have these. So if you're working in a non-private cloud or working on your own data center that doesn't have cloud software like OpenShift on it, I really suggest using the built-in load balancer, because it will help you automate things more quickly. That's really what it comes down to, is not just having things automated, but having them automated as soon as possible, because you don't want to start the snowball of doing microservices manually, because you will never get off that train. It will just keep going, and you'll be constantly deploying and managing things manually. So as all of these have built-in load balancers, they also have automation for scaling built in. So doing scaling automation is actually pretty easy. Amazon has one, Google Cloud has one, OpenShift has one, and they're all, there's an ASG, auto-scaling group in Amazon, autoscalers in other contexts. Use these built-in things because they automate things for you, which means you need to do less work. It's great. And these will understand what it means when a new instance comes online. Some things like the Amazon scaling group is a little dumb, so you have to do a little bit of extra work to get it to really be great. But this will handle that for you, so you don't necessarily have to worry about it. And conversely, it will understand what needs to happen when an application is ready to go away. So it will do that stop sending traffic, and it will wait until a certain signal gets sent in order for it to actually remove it. They don't just get killed. Service discovery, which is a slightly different take on load balancing, is something that I personally really, really like. And if you have the option of going with a traditional load balancer or service discovery, I'm a big fan of service discovery. So service discovery, like a load balancer, it routes to your healthy instances of your application. It's pretty standard. If you're doing this manually, your applications will have to register with them. If you're using something like Kubernetes, this happens automatically. But if you're in the realm of still using EC2 instances to do microservices, your applications will need to make an API call to service discovery saying, I'm ready. And these route via a conventional system. And what do I mean by that? So let's say you have services A and B and service discovery in between them. A wants to talk to B, so it sends a request to the service discovery with B in its path. So service A doesn't know where service B is, and service A doesn't care. It doesn't know a DNS name, it doesn't know an IP, it just knows that it can call the service discovery with B in its path, and that service discovery system will route it to B. Automatically, it'll change the path, and it is actually really nice, because then every single service you have only has the dependency on the service discovery. Yes, you're creating a single point of failure, but it makes things a lot easier, especially in the case that B gets unhealthy all of a sudden, and B doesn't want to have any traffic to it. When A makes that request, Service discovery denies it, but denies it in a known fashion. It denies it in a way you can usually customize to some extent. So you're not just getting random 500s. You're getting a known error that indicates that something is wrong with service B. This is a lot easier to debug. This is a lot easier to monitor. So the service discovery system knows health and can also trigger your scaling automation. If you're using something like Kubernetes or Consul or Nomad, they work really well for this and can do this automatically. Again, it's more infrastructure, but it's really, really useful infrastructure. But unfortunately, scaling is not our only problem when it comes to microservices, because scaling only solves so many problems. Sometimes scaling will go up, and then in like 5 minutes it'll go up again, and then in 5 minutes it'll go up again, and then in 5 minutes it'll go up again. And that's a problem. So scaling doesn't necessarily solve all of your problems, which brings me to the last challenge of microservices, which is debugging. And the thing about debugging is, first you need to know there's a problem. These are really complex systems, so surfacing information is a constant source of pain if you haven't done it right. So how do you know that there's a problem? Well, most people set up alerts. Alerts are great. I love alerts. Useful alerts are even better. I've seen things where like alerts will get propagated, but then like auto-scaling will kick in. So by the time you actually look at the alert, it's like, oh no, we're fine, we just created a new instance. I'm like, why did you alert me? You could handle this. So having alerts that are actually problems is really important. You don't want to get alerts for everything, because then you have the boy that cried wolf situation, and no one looks at the alerts, and then something's actually wrong and nothing happens. So you need to know what qualifies as a problem. And again, this will also vary per kind of application you're running. A standard API server will have a kind of a normal kind of issue. Something like a RabbitMQ cluster, again, will have a standard kind of issue in databases as well. So you track some of your standard things like we talked about before: RAM, CPU, latency, database writes, all that sort of kind of standard stuff that's going on. But also things like less obvious, like what I said earlier about the auto-scaling that happens every 5 minutes. Chances are that's a problem if you're not also getting significant increases in traffic, because that means your application has a bug causing it to trigger auto-scaling, whether it's using RAM, using CPU, having high latencies, and it's just going to keep going, and you're going to have more instances registered, you're going to be spending a lot of money. And it's just not something you want to just keep happening, because soon you're going to be having all of Amazon's inventory running your one application, which I don't recommend you do. You also can set up alerts for key performance indicators. If you're running in a system that's supposed to be really, really fast and using something like gRPC, which is really real time, it's supposed to be really low latency, really, really fast. If all of a sudden you're seeing 1 or 2 seconds between those things that should be taking 10 milliseconds, you probably want to alert on that as well. So it's being smart about knowing what your expectations are for your system and setting up alerts for that. And the thing about alerts is that they're for known issues, that they're for issues that you can imagine happening in your head or scenarios that have happened in the past. But that doesn't always cover everything. So in addition to alerts, you need to have dashboards, and yes, humans need to look at them occasionally. Because until you actually know what a certain kind of error looks like, you can't tell an alert to look for it. You can think about things really, really hard and be like, I think I found everything, but you're not. Something is always going to go wrong that you hadn't anticipated before. So you need to be able to watch it yourself, or just have the display up in your like office somewhere so that you can actually go through and keep track over time of what's going on. So imagine you just got an alert, you saw something weird on the dashboard, and there's this issue going on. Something looks a little weird. What do? How do you debug it? Well, we're all developers here, so our first instinct is to go to the application that looks like it's having a problem, right? One application has some sort of alert, you go look at that one. But here's one of the caveats, and this is, I know, a very controversial subject, but in my world, you want to pretend that SSH doesn't exist. So how do you debug your application if you don't SSH. Like, it's a thing. One of the reasons I say this is, as Mike mentioned, I used to be an iOS developer. iOS is a compiled language, and it comes with a built-in debugger. I can't tell you how many issues I've had to debug, because when the debugger is attached to a program, it runs slightly slower than when the program is running normally. So you get all sorts of race conditions that happen when you are not attached to the debugger that you cannot debug. So one of the things that, as I've been doing back-end stuff and working with other teams, it's been, just try not to use the debugger. What else do you need? Because if you are relying on that SSH access, what happens if you're trying to debug a server and you can't SSH into it? For whatever reason, whether it's a network policy, whether it's somewhat external to what you're working on, whether you're helping another team, you need to have other ways of debugging that don't involve actually modifying the application that's running. So your next best thing is logs. Logs are super important. They're super boring, though. Who likes writing log statements? But log collection and aggregation is an important part of your healthy microservices ecosystem, because you need a way to see what's going on in all of your different services. You need a way of comparing them. You need a way of seeing the history. All of that stuff needs to happen. This is another piece of infrastructure that needs to be added. And if, again, you're going for gold star, because we all love gold stars, you can also update your applications to have a configurable log level. I've seen this happen where you either have a configuration file that is periodically read from disk, or I've actually seen like private API calls where like you hit this one URL and it flips a switch. And this is useful because if you're debugging a system and let's say you're currently not logging the incoming requests to your API, but you're like, I think there's a problem with these incoming requests. They might be formatted incorrectly. If you're able to flip that switch and just start seeing requests, it will significantly decrease the amount of time it takes you to debug that issue. So if you can configure your log levels, do it. And so you're going on, you're debugging, you're inspecting your logs, and let's say you find a non-trivial issue. When you find a non-trivial issue, it's time to isolate that service because it's going to need to change. It's already causing problems, so it might already be isolated, but sometimes it's not. Sometimes if you have automation for that, it might not work, or you might have already had automation and it's working great. So all of this is because you want to avoid cascading failures. This is a big, complex system. Things are dependent on each other, and you don't want one problem with one application becoming several problems with several applications. So how do you isolate a service? Well, before you can isolate something, you need to identify what else is dependent on this service. So what parts of your system depend on another? If it's a really big, complex system, chances are you're not just going to be able to rattle off a name of 3 different things. You're going to actually have to go in and figure that out. And this is where, again, something that Chris mentioned comes into play, called request tracing. This is a pattern used to track traffic between your system, and it works holistically. So instead of trying to figure out what's going on where, you're actually seeing what parts of the system are dependent on each other and what specific parts you need to worry about right now. Other stuff we'll deal with later, but right now you care about these few pieces. And this often comes as a unique request identifier. Usually passed in as a header if you're doing REST. If you're doing something like gRPC, you can add metadata to tags. And this is added to every single request in the system. And that's really important, because if every system, if every application isn't participating in request tracing, you're not going to get the full picture. So this works much best as an overlay system. Another one of those single points of failure, but it's actually really good to have as a single point. And something that I want to briefly mention is open tracing. It is a request tracing standard that is open source under the Cloud Native Computing Foundation. And all of the major request tracing libraries that you'll find implement this. And one of the reasons I say this is because you want everything to be standardized. And if you use a standard, you can then have teams pick and choose the kinds of tooling that they want to use, instead of locking them into saying, well, you're only allowed to use REST APIs, and you have to use HTTP 1.1 because we're not dealing with case-insensitive headers, and it always has to look like this. That's a lot harder. So you can add it manually. It's going to be a lot more drift in the system in terms of how that's implemented. I mean, the IDs themselves might even look different for all you know. So you can add it manually, but adding an overlay system like request tracing to figure out what parts of your system depend on the other is really important. So now that you have isolated, now that you've identified everything in your system, you get to go and actually isolate it. And how do you do this? Well, circuit breaking is the predominant pattern for doing this. Circuit breaking works just like a circuit breaker in your house. That's where the term came from. When a circuit is closed, traffic is flowing between 2 points. When a circuit is open, traffic is not flowing. And the reason that circuit breakers have become so popular is that a circuit is a known point. It's a known state. If an circuit is open, you understand that. Your application can reason about it. The system can reason about it. And most importantly, when that circuit is open, there's no traffic going to the problematic application, so that gives it time to recover. If your application's in a crash loop, you want to stop sending traffic to it so you can actually do stuff with it and that it's not constantly crashing. So isolating it is really important. And circuit breaking can be done by an application or the system. Most of the predominant service discovery tools out there do this for you automatically. Netflix's Eureka does it, and as well as Kubernetes, and Console does it as well. And you can configure it. So if there are some applications where you're like, well, we want this threshold for failing the request to be this number, but in this other application we want it to be higher or lower, it's totally possible to customize that. And all of this is about failing gracefully, because things are going to go wrong. You don't want them cascading across your system. You don't want your system being unprepared for when things go wrong. You need to build your system knowing that things are going to go wrong up front. So in the process of doing all of this, you've isolated your system and you've identified the problem, and you go ahead and deploy a fix. And hopefully you're able to reuse a lot of the automation you already have so you can slowly start sending traffic to your problematic server. This is, again, one of the reasons that I really like the canary deployment method, because it already does this. So you can reuse the same automation, start slowly sending traffic to it to see if you actually fix the problem. You might have written tests. You might have tested stuff manually. But at the end of the day, until it's actually running in production, you don't really know, because systems are different. Your system in pre-production environment will actually be different than your system in production environment. Be using different servers, it'll be using different databases, things will be different enough that it'll cause problems. So if you're using something like canary deployments already, you can slowly ramp up traffic. Service discovery will also do this, it'll slowly ramp up traffic. And the built-in load balancers from cloud providers will also do this for you. So they'll see that, oh, hey, the service is registering as healthy, but let's not give it 100% of the traffic just yet. Let's just slowly ramp it up. So again, if you can use one of those built-in tools from a cloud provider, do. It will make your life a lot easier. Otherwise, you have to go in and update circuits manually and go into each application that you'd opened a circuit for earlier, and now you've gone in and closed them all, which effectively ramps back up traffic slowly. So you can still do it, but again, it's another manual change. So if you can do it automatically, definitely do. The reason I talk so much about manual stuff is, especially when you're in the beginning of your microservices journey, you won't have all of this automated yet. So only talking about what to do when things are automated leaves this gap where people are like, we're trying to do Y, but before Y, we have to deal with X. And so it gives you a little bit more insights on like the kind of baby steps you can take, even though they'll take more time. And then hopefully everything returns to normal. You've deployed your fix, you've ramped up traffic, your circuits are closed, everything's happy. But what if in the course of this, you figured out that your service, one of your applications, is not actually the problem? This is a big system, but there are also things that happen outside of your system under your control. So how do you know if you have an external dependency? And as much as we would like to think that our microservices and our systems only ever work together in like this closed little bubble, that's not true. Things happen elsewhere. So if you're going through the process of debugging a problem, how do you know if you're trying to debug something that is external? And we'll get to why this is a real big deal in a bit. So if you don't have access to logs, you have an external system, because you can actually try and figure out what's going on. If you don't have access to logs, you probably also don't have SSH access anyway, so hence logging is important. If you don't have access to source, again, external system, because you can't look at the code and see if it's throwing an exception when this one condition happens. You can't do that. But most importantly, a system or a dependency is external if you cannot deploy a fix. Like if you yourself as a person cannot deploy a fix. Even if it's the person that sits 2 desks over from you is on a different team, but if you can't see their logs and you can't deploy a fix, it's still external because they have a different set of priorities than you do. So they might be in the middle of a different issue, so they might not be able to help you. So you have to figure out what you can do in your little bubble to have a resilient system in the case that there's something external. So you have fewer tools at your disposal. Kind of sad, but it's the truth bit. So what you end up doing is mostly damage control. Every system has dependencies that are outside of it. That's just a reality that you have to accept. Closed systems are really, really rare these days. Even something that, like, if you get a fat binary from a vendor and you're just running it on your servers, that's also an external dependency because you can't deploy a fix without the vendor giving you a new copy. And you might have logs, but you can't see the source code. So it's really important to understand how to mitigate these kinds of failures. So how do you limit your impact? If it's an external API, especially a public-facing API, it probably has a status page. Those are great. Love status pages. And one thing that people might not like you doing, but I've seen become necessary in the past, is to monitor the status page. So you have automation that tells you when something else is having a problem so that you are alerted before your system starts to degrade, or you might get 2 simultaneous alerts and then you're able to correlate them. And if you're looking at that status page, shows no results, no errors, then you probably need to raise your issue with an external team, with an internal team, GitHub issues, email, Twitter, like whatever you want to do to get the message out that there's a problem, you need to do that because you are not going to be able to solve this problem, unfortunately. It's a sad day, but it is true. Because you want to keep your system healthy. So what is inside of your control when you're debugging a system, there's an external failure, you can't fix it, what do you do? Well, can't really do anything with logs, unfortunately. You can use request tracing. More and more public API providers will let you send a request ID header, and they will send it back to you. So in the case that there's some API request going to a third party, but then coming back in your system, you want to know about that, because then you have some other dependency that you might not think about is going to be affected by this being down. So you sometimes can do request tracing, and definitely check out the documentation, or if it's something that you're paying for, you can usually request that feature. You can also circuit break. Circuit break is kind of your #1 mitigation strategy here, because remember, an open circuit is a known state for your system to be in. It is not a great state, but it is a known state, and it is something that you're able to recover from in the case that something happens. Again, all this is about degrading gracefully. You don't want your system to have all sorts of big problems because like one third-party API is like having database connection issues. Like you don't want that to affect you. But then sometimes things go wrong that are a little bit different, and sometimes your infrastructure fail. Does anyone remember the S3 outage that happened last year? How many people were actually monitoring the S3 status page? Okay, I see like 3 or 4 hands. We take for granted that a lot of these cloud-provided infrastructure services are going to be up all the time, but they're not. Their SLAs are somewhere in like the 99.99 or 99.999. So you really, like, you can't just rely on S3. I mean, I think even S3's status page went down because it was in S3. Yeah, don't do that either. So sometimes those kinds of failures are going to happen. And again, it's really tough on everyone. If you're serving up a single-page JavaScript application from S3 and S3 goes down, like, you should have a backup plan. It might not be a great backup plan, but you should have one. And again, this comes down to circuit breaking. If you can, if it's something that you don't need to like totally like boots on the ground, fix it right now, if you can just be like, I'm just gonna like not call this for a while, do it. Otherwise, have a nice backup plan. Do something a little bit better. So to recap, when you're debugging apps internal to your system, things that you control, things that you can affect, you log, trace, and circuit break. But when you're debugging any sort of external part anything external to your system, you can trace sometimes, and you can circuit break. Circuit break is like super important when it comes to resiliency. I can't say all that enough. But as I start to wrap things up, you might have noticed a common thread through everything that I've said. I've kind of mentioned the same thing several different times in several different contexts. That's about metrics. It's about information. And it's about monitoring. Because you now have a distributed system. You don't just have one monolithic application. You have all of these different parts, and you need to know what's going on. So monitoring is all about gaining insights into your distributed system. And it's not free. It's not. There are people who are going to try and like sell you things and say, it's free if you do this. It's not going to be free. There's always a cost. Your applications need to be updated with things like health checks. Health checks are super, super, super important. And it's important to have them be more than like, I'm okay or I'm not okay. You need to actually have information in there, because that's the only way that information's getting out. Your infrastructure needs to be updated. There is a lot of infrastructure that needs to be in place so that you can have a really resilient and highly available system. So things like monitoring health checks, something needs to do that. All about gathering that information to, again, create confidence that your system is healthy, to create an ecosystem that is surrounding your microservices so that they can thrive. And this requires more metrics, sorry, and smarter infrastructure. And so I'm going to leave with this wonderful quote from the Cloud Native Infrastructure book by Chris Nova and Justin Garrison. And it's that infrastructure won't evolve on its own. People need to change their behavior and fundamentally think of what it takes to run an application a different way. So I hope after this talk, you all go out and build software to manage your software and build software to support a healthy microservices ecosystem. Thank you. Yay!
Thank you, Michelle.
Thank you.
Another hat and mug for you
Hat
as
and
well.
mug. Wait, what's this? What's this?
And a pen.
Oh, a pen. I didn't bring one.
So we try for, covering all the bases.
Thank you.
You can drink, you can walk outside now, hopefully, even in the cold.
Yeah.
And you can write. So
Yes, excellent. All my needs.
we're all set. We have a little bit of time for questions. Please don't ask your question until you have the mic, because we're recording this and we will not hear you on the video if you don't use the mic.
Hi, Michelle.
Hi.
Thank you so much for sharing your experiences. There's one thing that I wanted to ask you about a little bit more in detail, and that's this concept of a circuit breaker. Mm-hmm. Specifically, I work for a large organization that does microservices, but I'm not really seeing that circuit breaker. I mean, what it sounds like to me is you're saying something problematic is happening with your server, and it sounds like you're saying completely pull it out. And that's not something, I mean, I've definitely seen problems, but it's usually a rollback or roll forward situation. And so it makes it sound like completely pulling your service out is a common solution to this problem. So I'm just curious, like, in what kind of situations does this happen? Thank you.
Yeah, so circuit breaking is very configurable. So it's not necessarily pulling it out entirely. Sometimes it's just saying we're going to reduce the amount of traffic we're sending to this other service. Because if you're getting 500s or other random error codes, I saw a tweet today that someone was getting 502s. I don't think I've ever personally seen a 502. It's usually a 500. So it's not necessarily about completely always removing that traffic, but it's about letting your system be resilient in the case that that system needs time to recover, or if that system goes down. Because if there's put yourself in the shoes of the other person. If your application is having problems, do you want other people to continue to call your application while you're trying to debug it? No. So it's on both sides. It helps your microservices stay up and running more, and it also gives the people who are trying to fix their services, because chances are they're trying to fix it, it lets them have a little bit less pressure. And then if you're using something centralized like service discovery, it will be able to handle all of those mechanics for you. Circuit breaking can also be done at the application level. But then it's a little bit more involved Because like you might need, like you have one application that's circuit breaking in like 3 different applications, and you're gonna need to know what the fault tolerances are. And another detail of circuit breaking that I didn't mention, but is part of the pattern, is that once that circuit is open, you're pinging for health checks. Again, health checks come back in. Health checks are super important. So if your circuit breaking tool sees that health checks are now passing 9 out of 10 times, it'll close again automatically. So it gives you that time to recover, and it gives that isolation. So it's not necessarily just about like, oh, we never want to send traffic. It's just about making the system more resilient to failure and putting it in a known state versus having an unknown state of getting some random server errors, if that makes sense. You're welcome. Hopefully there's more questions during Birds of a Feather. Oh, there's one.
Hi, Michelle. Are you from the Twin Cities?
Oh, no, I'm in San Francisco.
Well, okay, I used to be in San Francisco as well. Number one, thank you for coming out on a cold winter day like this.
Oh, I love snow. Okay. I love seeing snow, I should say. I don't love being in snow. I love seeing snow.
I have a 2-part question. The first one's kind of a soft question for you. I noticed that you're a Doctor Who fan. Season 11's coming out. Do you know when they're going to deploy it?
Oh, I wish. I do not have any contacts at the BBC, unfortunately.
Okay. And my second question, though, is really, I'm not sure if you and Chris have been banned from saying the word blockchain in this conversation that we're having today. But, you know, when I look at microservices, I do consulting in microservices, and one of the things that comes up is blockchain because it's so similar. We have similar languages like C++, Java, there's openness, there's distributive, there's APIs. Since you're with Capital One, and because cryptocurrency and blockchain is kind of moving into the fintech area, where do you see blockchain, microservices? I mean, I think they're merged already, but where are you at with that at this point?
Chris just did a thing, and I'm like, okay, that sounds like, that's a heavy question there. To be honest, I don't do much with cryptocurrencies. Capital One is a really big organization. The last official count I heard was we were over at 45,000 people. So there's a lot of people working on a lot of different stuff. They do have a lot of similarities in terms of operational aspects to them with like the distributed systems and all of that stuff. But a lot of it comes down to the applications of it. Blockchain is being used for so many different things. And actually one of my former coworkers left Capital One to do a blockchain startup to do healthcare and like do health related activities. I don't exactly know what the details are. So they are related. And blockchain might use a lot of the microservices patterns that you see. But fundamentally, they're different. Microservices are about being able to operate any large-scale distributed system, and then the blockchain is a really specific application of that. So in my mind, that's kind of how I've been conflating the two.
Great, hi. I wonder if you could expand on something you briefly mentioned in terms of monitoring and metrics, and as the next level of observability to basically allow developers to just see how their apps are working within that context, not necessarily because there's something wrong, but to get some idea of really what's going on, and then later help detect issues.
So there's a couple of different things that I've done and have seen people do. Chaos engineering is a big thing out of Netflix. My team uses a lot of the Netflix stack, so it's something I'm really familiar with. And there's actually a talk later on intentionally having your system fail and like knowingly like have your system fail. That's one of the ways which you can do in pre-production or production. Netflix does it in production, which I think is an interesting choice. I don't know if I'd want to be on one of those teams personally. So that's something. I've also seen things where instead of doing like a canary deployment where you have like, you start routing traffic and it's like real honest traffic, I've seen tools that let you actually duplicate traffic. So instead of a new service taking traffic and like actually being part of the system, you're just kind of monitoring it to see, hey, is this going to work? And there's like all sorts of different things you can do, especially if you add in some more data science-y aspects, like traffic shaping. So if you're trying to do like bot detection, you can actually train ML models to see like on the normal patterns of traffic that you expect, and they can detect anomalies. So there's a lot of different things going on, and a lot of it depends on the kinds of goals that you have from doing this kind of work. Does that answer your question? Okay, cool.
Hi, I'm curious about how does Capital One manage compliance and validation that the code that you're releasing is good?
Very carefully. I don't know about that much in detail in terms of like overall process and stuff. I mostly know what my team does day to day. And we have certain requirements around things like scanning, so our code needs to be scanned. There are certain kinds of vulnerabilities that will be checked. We have requirements around how old our like AMIs are used. So we have Amazon machine images that are custom built. There's a certain, like you always have to be running a certain level or above so they know about security concerns. And there's like a whole like checklist of things you have to do. Having your code reviewed by someone else. We have separation of duties so that the person who's writing the code can't be the one to deploy the code in a manual deployment environment. We do have continuous integration, in which case it's usually someone that's not the application developer writing the underlying infrastructure. So there's a lot of different things we do, but in practice it actually isn't really that different. But my team doesn't necessarily work on super heavy stuff. We do have concerns for PCI encryption, and so we have gone through and made PCI environment set up, and everything's up to code, and there's extra special training that people have to do, and we have extra logging, so it's not just like, our applications don't just like log that like this thing happened, we also log that like Michele deployed to this service on this date with like this change set. So there's a little bit more logging and stuff. Honestly, it's not as invasive as it probably could be, so I don't find it is any harder to do. It just takes a little while to get everyone used to those kinds of processes. Does that help? Cool.
One more question.
Hi, Michele. So my question is more about like you create a service and then you have a certain amount of traffic that comes in. But then when we come to a math problem of how do I break it into different servers and come to a problem of like, okay, I have to, out of this service, this is the amount of traffic that goes to each of these servers. How do I actually define that? Or what is the tool or what is that thinking process to actually define these servers?
Yeah. A lot of it is having a good understanding of when you're going from a monolith to microservices. Like when you're building a monolith, there's going to be certain components that are imported everywhere. There's going to be certain classes that are used all over the place, and those become signals. I love using login as an example because pretty much every application these days has login. So if you have if you're trying to create a login service and break that out from your monolith, there's going to be a lot of other things that talk with that login service. So you're going to be able to tell really quickly that that's going to be getting a lot of traffic. Versus if you have something that is kind of off on its own, it might use login and a couple other things, but nothing uses it. That library isn't imported anywhere. That's a good indication that it's going to be low. And another thing about using this automation is that it's really easy to change. So if you're deploying stuff for the first time and you're like, well, I might need 5 copies of this, I don't know. You might be able to deploy 5 copies, and then all of a sudden you see, hey, 5 isn't enough. It's really easy to go in and just pump that number higher. And conversely, it's a lot easier to say, we deployed 5, but they're all running at like 0.3% CPU. We can definitely make them smaller. So it's part of the whole constantly changing system thing. And if you're using something like Kubernetes, which I've been working a lot with lately, it's really great because it lets you set a minimum and a maximum. So you can say, I want at least 2 of these running, but I might need 10. And the system will be able to decide for you how many to have. So if you're not sure, using a tool that has that understanding will also help you migrate to microservices. Cool. Thank you very much.
So next we have our breakout sessions. They start at in 5 minutes. And we have a change. Unfortunately, Joel Tosi, who is coming in from Chicago, his plane got diverted to Milwaukee this morning because apparently they're not landing flights right now at MSP. So we're going to run the costs of microservices, because I think that's an important topic, twice. And the first instance of that talk will be at the Johnson Great Room. So I apologize. And Joel apologizes, but some things are out of our control. So the cost of microservices will run right back here. Thank you. Oh, also, turn in something for birds of a feather if you haven't already.